Good. I got a new drawing tablet, so
Oh, yeah?
I should not have the problems that I've had here lately.
Oh, okay.
Yeah, seems to solve the difficulties. I don't know whether you experienced those with me or not, but my drawing tablet was kind of going schizoid on me.
Yeah, I remember.
Okay, well, that shouldn't happen again. So what are we doing tonight? Did you send me anything?
No, I think I can verbalize it all.
Okay, what do you got?
Okay, so, let's see. Use graphs and tables to find limit x going to infinity and then limit x going to negative infinity, and then identify all horizontal asymptotes.
Okay.
And then the first one is sine 2x over x.
I want you to use graphs and tables.
Yeah.
Well, all right. I could put that into Wolfram Alpha or PI Inspire, and the definition of a horizontal asymptote is what the function does as x goes to infinity or negative infinity.
Okay. So it's just its limits?
Well, let's say that, let's take the more simple one, which is sine x over x. As x goes to 0. Well, it's not real clear what that does from looking at the function, because as x goes to 0, you have 0 over 0, which is indeterminate. But if you look at the graph, oops, excuse me, it, as x goes to 0, the function goes to 1. And as x goes to infinity, in other words, that direction, the function appears to go to 0.
Right.
And as x goes to negative infinity, the function appears to go to 0.
Okay.
Now, the question is, would sine of 2x over x be any different? Well, let's look at the sine of 2x over x. They teach you in limits that the sine of x over x as x goes to 0 is what?
1.
Right. Okay. Well, this is a little different because x is going to infinity. So clearly the sine of x over x as x goes to infinity would be 0. Now the question is, what does sine of 2x over x do? Well, one way we can look at that is to multiply top and bottom by 2. Well, there's the 2 there. There's the 2 there. Now, clearly, if we were taking this function as x was going to 0, we know this part's 1 times 2, so the limit would be 2.
Okay.
So if I were to graph that, it would look very similar to what I have now. In other words, the 2 is really a horizontal factor. It's not anything else, but it would go up to 2. But it would still go to 0 as we went to infinity or negative infinity.
Right.
And you can kind of see it from the graph. I guess there's really no other way to figure this out other than when you think about it. Let's think about this. As x goes to infinity, the denominator blows up.
Right.
The numerator bounces back and forth between 1 and minus 1. Well, if I have some number, c, that's between 1 and minus 1, and the denominator is going to infinity, that whole thing's going to 0. I don't care what c is.
Mm-hmm.
With limits, if the denominator blows up and the numerator stays constant, the limit's 0. If it's the reverse, let's say we have a number over x and we're taking the limit of that as x goes to 0, well, that's completely different. Now the numerator stays constant, the denominator gets closer and closer to 0, the limit of that thing is infinity.
Okay.
Or they might say undefined.
Okay.
They like to use those words interchangeably.
Mm-hmm.
All right. What else? What other function?
So both infinity and negative infinity, the answer is just 2, right?
No, it's 0. In other words, this is what our function looked like.
Oh, okay, because it's going to infinity in the... Okay,
yeah,
now that makes sense.
I'm sorry if I confused you.
No, yeah.
Going to 0, the limit would be 2.
Okay.
But as it's going to infinity, the limit is the horizontal asymptote, which is y equals 0.
Okay.
That's kind of the definition of horizontal asymptote. What the function does as it approaches positive or negative infinity.
Okay. Okay, so I have 3x to the third minus x plus 1, and then all over x plus 3.
And we want the limit as x, let me guess, goes to minus 3.
It's actually infinity still.
Oh.
Yeah.
Well, now
and then it's like the use graphs and tables to...
Okay.
Yeah.
But we're also talking end behavior. When we talk about x going to infinity, we're talking about right-hand end behavior. And when we talk about x going to negative infinity, we're talking about left-hand end behavior.
Okay.
Well, end behavior is determined only by the highest degree polynomial, which in the numerator is 3x cubed. In the denominator, it's x. I don't really care anything about the rest of those, no matter what they are.
Okay.
And these two reduce to that, right?
Right.
So what's the limit as x goes to infinity?
So you use the exponent?
Well, no, think about that. As x gets infinitely large, what happens to 3x squared?
Doesn't that just get infinitely larger too?
So that limit is also infinity.
Okay.
Now, on this problem, did they also ask you about negative infinity?
Yes.
Okay. What happens to 3x squared as x goes to negative infinity?
That would be just negative infinity?
No, because negative infinity squares to be positive.
Oh,
In
so
other
it's the
words,
same
the way
thing?
to look at these is to go ahead and substitute infinity. They hate to do this because that makes it look like infinity is a number.
Yeah.
If I take negative infinity and square it, it's positive. If I take negative infinity and cube it, it's negative. It stays negative. Okay? So the limit of 3x squared, I mean, think about what 3x squared looks like if we were to graph it. It's a parabola.
Right.
Well, as I go in this direction, it goes to positive infinity on the y-axis. And as I go in this direction, it goes to positive infinity on the y-axis.
Okay.
But if I'm looking at a function that is, say, x cubed, as a different eraser. I'm not used to it. If I'm looking at x cubed and I want to know what its limit is, well, x cubed kind of looks like this. You can see from the graph that as x goes to positive infinity, y goes to positive infinity.
Okay.
As x goes to negative infinity, y goes to negative infinity.
Okay.
So that the end behavior definitely can be affected by the power of the exponent.
Right.
But it's always the differential power. In other words, we started with 3x cubed, but we were dividing it by x.
Mm-hmm.
So that became 3x squared. And that is what we wanted to look at in terms of end behavior, is the ratio of the highest degree term in the numerator divided by the highest degree term in the denominator.
Okay. All right. So I have 2x minus 1. And then all over the absolute value of x minus 3. Oh, the 3 is on the outside of the absolute value.
And we want the limit of this as x goes to infinity again.
Mm-hmm. And negative infinity.
All right. Let's take a simple example.
Mm-hmm.
Let's take 3x squared over 2x squared. If I'm taking the limit of this thing here as x goes to positive infinity,
Mm-hmm.
because the exponents are the same in numerator and denominator, it goes to that ratio.
Okay.
If the denominator is bigger, in other words, if it's cubed instead of squared,
Mm-hmm.
well, clearly the denominator is going to blow up, and this whole thing's going to go to 0. You see
Okay.
why? If I take 1 over x, the limit of that as x goes to infinity is 0, plus or minus infinity.
Okay.
In other words, if the denominator blows up and the numerator stays constant, the whole thing's going to 0. Now, switch the exponents.
Mm-hmm.
Instead, let's make the numerator the bigger one. I kind of like my old eraser. I'm a lot better. I wonder if I can get it back.
Yeah.
Stroke, that's what I need. Yeah, there we go. If I were to make this 3x squared over 2x,
Mm-hmm.
and I wanted the limit of that as x goes to positive infinity, well, clearly the numerator, I can cancel one of those x's, and I'm left with an x in the numerator, so the whole thing's going to infinity.
Mm-hmm.
So the only time, in other words, either the numerator blows up over the denominator, and the answer is infinity, or the denominator blows up greater than the numerator, and then the answer is 0.
Okay.
Or the coefficients are the same, like that.
Mm-hmm.
In which case, the limit is the ratio of the coefficients, 3/2.
Okay.
Okay, now let's look at your problem. Because the degree in the numerator and the denominator happens to be the same. That's 2x, and that's x sometimes. It's either x or minus x.
Right.
So the very first thing we can see is that these numbers have no bearing on the answer.
Okay.
Words, we're analyzing 2x over absolute value of x.
Okay.
Well, as x goes to infinity, that's positive, the absolute value doesn't matter, so I really have 2x over x. So that limit is 2.
Okay.
But when x goes to negative infinity, well, now the numerator becomes negative and the denominator is positive. So it goes to negative 2.
Okay.
As x goes to negative infinity.
Okay.
And these absolute value ones tend to be the tougher ones, but the way to look at them as piecemeal. In other words, this function you gave me is 2x minus 1 over x minus 3 whenever x is greater than 0, and it's 2x minus 1 over negative x minus 3 whenever x is less than 0. Well, so when you go to positive infinity or negative infinity, positive infinity is going to go to 2, negative infinity is going to go to minus 2.
Okay.
All right.
So what would the graph look like for that?
Well, think for a moment. I guess the best way I can figure that out is to put it into Wolfram alpha. Let me go ahead and do that. I've used Wolfram alpha with you, haven't I? Absolute values are always a little tricky. This was 2x minus 1 divided by absolute value of x plus 1, minus 1, it doesn't matter, but
minus 3.
minus 3.
But it's on the outside of the absolute value. Oh, yeah.
All right, let's see what this gives us. I never know if I've gotten it in correctly. No, I didn't. I think I need parentheses there. Let's see if that does it. Yeah, there we go. The input looks right.
Okay, yeah.
So the graph, oddly enough, looks a little strange. Obviously, x cannot be 3 or minus 3. At 3 or minus 3, we're going to have a vertical asymptote because the denominator will be 0. That's why you see both vertical asymptotes at 3 and minus 3 here. But in between those vertical asymptotes, this is what the graph looks like. And you can kind of see that as, well, can you or not? It's not so easy. So as x, in other words, this is a repeating thing.
Right.
Well, no, it isn't. I'm sorry, it's not. They didn't expand this enough. If I had the ability to zoom out, you would see that this is not a repeating thing. There is not a vertical asymptote at 3, 6, 9, and so forth. In fact, the rest of this graph is hyperbolic in nature.
Oh, okay.
So we can see that, well, we can't really from the graph, but there's a horizontal asymptote at 2 on the right side, and there's a horizontal asymptote at negative 2 on the left side.
Okay.
You can imagine it. Can't see it from this one. If you graph that on your calculator, what do you have, an Inspire or a TI-84?
An Inspire.
if you graph it on an Inspire and zoom out enough, you will see that this is hyperbolic. In other words, that thing is going to approach the horizontal asymptote 2
Okay.
on the right side, and you can, even from this graph, you can tell that it's approaching a horizontal asymptote on the left side also that's a different horizontal asymptote. It's at -2.
Okay.
All right. So I think that takes care of that problem.
Yeah.
What else we got?
Okay, so the absolute value of x over the absolute value of x, and then outside of that plus 1.
Okay, so this function is x over x plus 1 whenever x is greater than or equal to 0.
Mm-hmm.
And it's x over, now it's minus x over minus x plus 1 whenever x is less than 0.
Mm-hmm.
So as we go to positive infinity, in other words, if we want the limit of that as x goes to positive infinity, what is it?
So would that just be positive 1?
Correct. Because all we care about is the ratio of those coefficients, which is 1 over 1.
Mm-hmm.
And as it goes to negative infinity.
And then that would be negative 1.
Huh?
Negative 1, yeah.
Positive 1.
Oh.
In other words, they're both negative. Right?
Right.
So the ratio of the coefficients is negative 1 divided by negative 1.
Oh, okay.
I actually think Wolfram Alpha does limits also. Let's just see. If I put in the limit of the absolute value of x over the, let's see what happens. The limit of ABSX divided by ABSX. I think it assumes infinity. And notice it gives you both, since I didn't put in what x was going to.
Mm-hmm.
But as x goes to 0, it goes to 1, and as x goes to negative infinity, it goes to 1, and as x goes to positive infinity, it goes to 1.
Mm-hmm.
And it really wouldn't have any, in other words, if I put in the plus 1 there, let me do that. I'm going to have to add some extra parentheses. That's not going to change anything.
Okay.
Still 1, 1 at positive infinity and negative infinity.
Okay.
And you can see what the curve actually is looking like up close. Is that's going to eventually approach the horizontal asymptote at 1,
Mm-hmm.
both on the right and the left.
Okay.
What else?
Okay. So x over x minus 2.
I'm sorry, what was the numerator?
X, just x. And then x is approaching 2.
Okay.
And then you're just supposed to find the limit.
Yeah. The first thing you always want to do on these limit problems is just go ahead and substitute. So if I substitute, I end up with 2 over 2 minus 2, right?
Mm-hmm.
Which is 2 over 0. What is that limit?
0.
No?
No. Oh, infinity.
Yeah. In other words, if the denominator's blown up, just so you can see it, let's take 2 over 1 equals 2. 2 over, I'm going to let the denominator get smaller. Now I'm going to get it smaller still. Now I'm going to get it smaller still. You can see what's happening. As the denominator gets closer to 0 and the numerator stays the same, the result gets bigger and bigger and bigger and bigger, such that as the denominator goes to 0, the whole thing goes to infinity. So these are actually easy problems. In other words, the ones that go to a number over 0 or 0 over a number. The only difficult ones at all are a number 0 over 0. Let me give you a difficult one. What's that go to?
The 2 over 0?
By direct substitution, it's 0 over 0.
Right.
But if we algebraically play around with this, it becomes x minus 1 times x plus 1 by factoring the numerator. Now, that x minus 1 cancels with that, and as x goes to 1, this whole thing goes to 2.
Okay.
So what started out as 0 over 0 ends up as just x plus 1. So the secret to the difficult limit problems are, all of the difficult limit problems are 0 over 0. There isn't a single limit problem that's not 0 over 0 that's hard. Every other one is either a number over 0 or 0 over a number. And you know what both of those do. So 0 over 0 is the only ones that are hard, and there's various ways to attack them. The most common is by factoring, like we did in this problem here. There are other ways, and in fact, notice the one they tell you to memorize. That's 0 over 0.
Right.
But they tell you that limit is 1. They don't tell you why, other than they give you a graph of it.
Right.
But it is 1. Whereas 1 minus cosine theta over x, as x goes to 0, that limit, which they also tell you to memorize, notice that by direct substitution I have 0 over 0, but that limit is 0.
Okay.
Okay? And again, you can graph that to prove it to yourself, and there is higher levels of calculus where you can show why this one is 1 and why this one is 0. But when you're just starting calculus, they have to start you somewhere, and they started you with limits. And you can't really get out of limits without confronting that right there.
Right.
And since they don't know how to prove it to you, they just tell you to memorize. And, and then 6 months later in calculus, they'll show you why that limit is equal to 1. There's something called L'Hopital's rule, where when you have 0 over 0 or infinity over infinity, you can take the derivative of the numerator and the derivative of the denominator, and that'll tell you the answer. But that's advanced calculus, which they can't really start you out with. So
right.
it's kind of a catch-22 with calculus.
Yeah.
What else?
Okay. I have x over x plus 3 And then x is approaching -3 from the positive side.
So you're familiar with positive and negative sides on limits.
Right, yeah.
If I were to graph that thing, I've got a vertical asymptote at x equal -3, right? In other words, no way, shape, or form can x ever be equal to -3. Well, I have a horizontal asymptote at where? What's the horizontal asymptote if I graph that? Remember what a horizontal asymptote is. It's what x is going to approach as x, it's what y is going to approach as x goes to positive infinity.
Is that just 1?
Yeah. So there's my grid for graphing this thing. And it's hyperbolic in nature. And
right.
So it's going to look something like that. Okay? And so if I look at that graph, what happens as I approach -3 from the right-hand side? What does the limit go to?
-3?
-3 from the right-hand side. And the way to view this, I should have drawn the function in a different color than red. Okay? Let me do that, just because it's a little clearer if I do that. So this is my function. And if I want to know what this function is doing as I approach -3 from the right, well, I'm starting on the right, I'm approaching -3, you see?
Right.
What's y going to?
Positive infinity?
Correct. Now, as I approach -3 from the left, what's y going to?
Negative infinity.
Correct.
Okay.
The reason I don't like to use the blue is because it's so thin. Thickness of the red there. But just for review on that one, obviously by direct substitution, well, first of all, let me ask you a question. What's the limit as x approaches -3?
It doesn't exist because they're not the same.
Exactly. And that's the only thing that is required for it to exist, is that they have to both be the same. If they are different, it does not exist no matter what. If they are both the same, that's the limit. Okay? Now, by direct substitution, if I were to say, let's just approach -3, we would have -3/0. Well, that's clearly infinity. Maybe that's negative infinity. It depends on whether you approach it from the left or the right, whether it's negative infinity or positive infinity. But you have a number divided by 0, which is infinity. It still requires you to put the sign on it. And you can see from the graph that one approaches positive infinity and the other approaches negative infinity. Another one that's kind of interesting. Y equals 1/x², which is kind of hyperbolic in nature, but not quite. What is the limit of that as x approaches 0 from the right?
Positive infinity?
What is it when I approach 0 from the left?
Positive infinity again.
So does it exist at 0? Yes, it does. That's about the only thing you can say about it. I'm not sure that you can say the limit is infinity, because that tends to imply that infinity is a number.
Right.
But you can say the limit is undefined, which
Mm-hmm.
means the same as infinity, but does not mean the same as does not exist.
Okay.
Those three terms do not mean the same. Infinity can mean the same as undefined, but DNE merely means that the limit from the left and the limit from the right are not the same.
Okay.
So the limit doesn't exist. But in this case here, the limit definitely exists. One might argue whether it's infinity or not, but it exists. In other words, it's the same from the right or the left.
Okay. Okay. So I have integer x over x as x approaches 0 from the left side.
It's the greatest integer function, right?
Yes.
So as we approach 0 from the left side, what's the limit? The graph. I'm assuming this is still part of use a graph or table.
Yes, yeah. It's 0.
No, it isn't. As I approach it from the left, I'm coming from this direction.
Oh, okay. So is it -1?
Yes. And as I approach it from the right, I'm coming from this direction.
So that's 0.
Correct.
Okay.
Greatest integer function is a bit strange in that regards. And a lot of times when they first teach it to you, they don't teach you what it does to the left of the y-axis. They only draw it for you when x is positive. But to the left of the axis, it looks just like the rest of the staircase.
Okay.
But there's a difference. When you have x equal -1/2, the greatest integer of -1/2 is -1. It's not the next positive integer.
Okay.
What else?
Okay. So I have find the vertical asymptotes of the graph and describe the behavior of f of x to the left and the right of each vertical asymptote. And then the first one is x squared minus 1 over 2x plus 4.
All right. Where's the vertical asymptote?
Okay. So if the top is greater than the bottom, doesn't that mean infinity?
Well, no. The vertical asymptote is always where the denominator is 0.
Okay.
What value of x makes the denominator 0?
-2?
Yeah. So there has to be a vertical asymptote there in this graph.
Okay.
Now, when we're to the right, the numerator blows up.
Okay.
This was the limit. The full question was, describe the behavior left and right of the asymptotes. Well, as we approach -2 from the right, the numerator is positive.
Okay.
The denominator is getting closer and closer to 0, but it's also positive. In other words, let's plug a number minus 1.99, okay?
Okay.
If we plug that number in for x, we're approaching it from the right, correct?
Okay. Yes.
And we can see that the denominator is getting close to 0, but it's getting close from a positive side.
Right.
Which means this has to be infinity.
Okay.
It's going to look like that. And clearly as x, no, hold it, it's not going to quite look like that. As x goes to infinity, the numerator blows up, so it's got to go to infinity. So I haven't drawn that quite right.
Mm-hmm.
Let's see, let's plot some points. When x is 0, I have minus 1/4. So that point's on there. Clearly we're going to infinity as x approaches -2 from the right, because the numerator is -2 squared minus 1, that's a 3. This is 0, we're going to infinity. Now, when x gets big, the numerator blows up, so this thing has to turn around and go something like that. Now, from the left, we would be starting with a number like that. Well, notice the numerator stays positive because it's an x squared.
Right.
The denominator approaches 0, but it approaches it from the negative side. So that's going to be a negative infinity.
Okay.
And something like that, I think. So let's see, as we approach from the right, we're going to positive infinity. As we approach from the left, we're going to negative infinity. Just for the heck of it, let's graph that. I don't think my graph is correct, but it's not that far off, I don't think. X squared minus 1 divided by 2x plus 4, and I'm going to need some parentheses on the numerator also. Notice our vertical asymptote at -2. Yeah, how does that compare with the way I drew it? It goes to negative infinity as we approach from the left, but then as x goes to negative infinity, yeah, this whole thing has to go to negative infinity. I should have realized that.
Okay.
So it doesn't look like that. It looks like this. More. Still comes up from negative infinity, but then it does something like that.
Okay.
Yeah, the key thing, their question regarded what happens at the vertical asymptotes, not so much what's happening as x goes to infinity or negative infinity.
Okay.
Right. All right.
Okay. So same, like looking for the same thing. 1 minus x all over 2x squared minus 5x minus 3.
I want the limit as x goes to what?
We're just looking for the vertical and then... yeah.
Right. Same thing,
yeah. Yeah.
So if we factor the bottom, which is going to tell us where our vertical asymptotes are, and what is it? It's going to have to be minus 3 plus 1.
Okay.
And that gives us a middle term of minus 5x. So, where are my vertical asymptotes? Makes the denominator 0.
Right. Would that be
What makes
3?
that? Well, that's 1. In other words, that makes that part of it 0. What makes 2x plus 1 0?
Let's see.
Set it up as the easy way to solve these is just set it up as an equation.
Okay.
Okay. Now solve it.
Oh, okay.
X equal minus 1/2. So I have 2 vertical asymptotes. Where is my, do I have a horizontal asymptote? Did they teach you about that?
Wouldn't it be 0?
Yeah, if the numerator highest degree is less than the denominators, then the horizontal asymptote is always at y equals 0.
Right.
Now there's my grid to graph this thing. And I know the graph is going to look something like this, probably over here like that, and then in the middle it can do most anything. Sometimes it does that, sometimes it goes up and turns around and comes back down. And I may have the quadrants off. In other words, I may not be in this first quadrant here, I may actually have it backwards, where it's in that quadrant and that quadrant. And I would have to tell by plugging in some values. In other words, if, that's at positive 3, excuse me. If I plug in x equal 4, well, what do I get? I get negative 3 in the top and I get positive in the bottom. So I've got to be below the y-axis when x is greater than 3. So I have definitely drawn it incorrectly.
Okay.
I need to draw it in this quadrant here. And almost certainly there. And I still don't know quite what's going on in the middle, so let me erase that line. But at this point, I'm relatively certain that I've got the outsides drawn correctly. If I let x equal minus 1, numerator is positive, denominator is also positive. So I would have to be above the y or the x-axis, and I am. And that's really the best way to determine it. If you can't actually graph it on a calculator, plug in values to the left and right of your vertical asymptotes, and that'll tell you what part of the grid you're in.
Okay.
So there's no doubt in my mind now that we got most of this drawing correct. Now, especially if the only thing they want to know is what's happening to the left and right of the asymptotes. Well, if I take the limit of the function as we approach negative 1/2 from the left, what is it?
That would be positive infinity.
And if I approach positive 3 from the right, what is it?
Negative infinity.
Okay. So the only question is what's going on in the middle, and they want to know that. Well, let's approach positive 3 from the left, 2.9, right?
Mm-hmm.
See, it's either going to be positive or negative infinity.
Okay.
The numerator is negative. The denominator, well, that one's positive, this one's negative, so the denominator is negative.
Okay.
So it must be positive infinity.
Okay.
Okay. Now, to figure out what happens when I approach negative 1/2 from the right, let's put in a number of negative 0.4.
Mm-hmm.
Well, the numerator is positive. That's positive, and that's negative.
Mm-hmm.
The denominator is negative, so it's going to be negative infinity.
Mm-hmm.
So that's what that graph must look like. If I were to plug that into Wolfram Alpha, I'm 100% sure that that's what it looks like.
Mm-hmm.
And that tells us the behavior of the function on both sides of both vertical asymptotes.
Okay.
And it also, in other words, you could do this problem one of two ways. You could graph it and then answer the question.
Okay.
Or you could do it the way I did it. I didn't really have to graph it to answer the question. I just had to plug in values that were close to our asymptotes.
Okay.
Like in one case, I could plug in plus 3.1, and then I could plug in 2.9. I know I've never seen a vertical asymptote where it didn't approach either infinity or negative infinity, right? I mean, that's the nature of vertical asymptotes. And the only question is to determine which one it approaches. In other words, as we're coming from the right, are we approaching negative infinity or positive infinity? Well, you can figure that out by plugging in a number slightly to the right if you want. If I plugged in 3.1, I would end up with a negative sign.
Right.
If I plug in 2.9, I'm going to get a positive sign.
Okay.
Same way on minus 1/2. In other words, the other way to think about limits as you approach from one direction or the other is to plug in numbers that are slightly to the right and left of your important x values.
Okay. Okay.
Probably got about time for one more.
Okay. So, okay, in parentheses, 2 over x plus 1.
Like that?
Yes. And then end parentheses. And then another set of parentheses, 5x squared minus 1 all over x squared. And then end parentheses. And it says find limit x approaches infinity and then x approaches negative infinity.
Okay. As x approaches infinity, what does the left side approach?
Would that be 0?
Well, this part be 0.
plus 1, so 1.
1, exactly.
Okay.
And as this side, this part in the parentheses, approaches infinity, what does the limit approach?
Infinity? No, negative 1.
The ratio,
Well,
the powers of x are the same top and bottom. So whatever the ratio is of the coefficients, in this case 5 over 1.
okay.
So that limit is 5 as x approaches positive infinity.
Okay.
Okay? Now as x approaches negative infinity, doesn't change that one. This part that I have circled here is still going to 0.
Yeah.
Right? So that's still going to 1.
Okay.
And this part over here, it's not going to change because they're both x squareds. So the fact that I'm going to negative infinity, that thing is still going to 5.
Okay.
So that limit is also 5.
Okay.
Yeah, whenever you have fractions like this, I mean, you can zero out any part of the fraction where the denominator is going to blow up. Unless, of course, you have the same power in the numerator and the denominator, and then it's the ratio of the coefficients. Now, even if it was 5x cubed over x cubed, notice that x goes to infinity, that thing still goes to 5. And as x goes to negative infinity, that thing still goes to 5. Because the numerator is going to go to negative infinity and the denominator is going to go to negative infinity. Well, that equals positive infinity. Or positive 5, excuse me.
Yeah. Okay, so what would the graph just be like x over x plus 3, like those graphs?
Well, let me think about that for a second. We've got an asymptote at 0. Only. So it's hyperbolic in nature because the denominator is actually a bigger power than the numerator. If you multiply these two things out, the denominator is x cubed. The numerator never gets above x squared. So the graph of it trying to figure out if I can even figure out what it is. Probably not without actually graphing it, other than I know there's a vertical asymptote right there.
Right.
And since it's hyperbolic in nature, it almost certainly looks something. We have a horizontal asymptote at that because the denominator is a higher power than the numerator. So almost definitely it does something like that. Let's see if that yeah, as x goes to infinity, this whole thing goes to 0, and as that's not what I said, was it? I said as x goes to infinity, the whole thing goes to 5. Well, the right part of this thing has a horizontal asymptote at 5. But after I multiply it together again, I would have thought that that horizontal asymptote would be 0. Maybe it's not, though, because clearly the definition of horizontal asymptote is it what it is as x goes to infinity and negative infinity, and clearly that's 5. So I haven't drawn it correctly. We must have a horizontal asymptote at 5, not at 0. And then the thing is going to go something like this. And I would have to graph that to verify it, but it'd take me too long to even type that in. But you could certainly verify it if you wanted to by putting that into your grapher, which is, I suspect that's what you want you to do anyway, right? On all of these?
Yeah, I have to have
really
a picture of it.
Use your calculator. And we took a little bit of a different approach on them. We tried to figure out what they would look like and then looking at the graph do it. So the only difference we did is we tried to graph them manually in all instances except this one. And this one I think is now correct, even though I got my horizontal asymptote off initially. But you can see that as x goes to infinity, we're going to 5, and as x goes to negative infinity, we're going to 5. All right, Emma. You good to go?
I'm good, thank you.
Okay, I'll talk to you next time.
Sounds good.
Bye-bye.
Bye.